So now we will talk about modular arithmetic or the equivalent notion of congruences. So this goes back to remainder that we obtained on division. Okay, so division on remainder, recall, was the following. If you had a number d, a natural number d, and you had any integer n, then we could divide n by d to produce a quotient and a remainder, and the remainder had the following property or the following requirement, that it is a number between 0 and d minus 1. Okay, so the remainder can be 0, 1, 2, 3 all the way till d minus 1. So these are the possible values of the remainder. Okay, so there are d different remainders possible. So observe that the remainders, the number of possible remainders are d. So possible remainders are d in number. Okay, so now here's a notion. We say that two numbers are congruent modulo d. So we say that two integers n and m are congruent modulo d if they leave the same remainder on division by d. Okay, so if they have the same remainder on division by d. Okay, and there is a notation for this which is again very useful. So the notation, if m and n are congruent modulo d, we would write this as m, this 3 lines here, and we read this as m is congruent to n mod d. So that is how we denote this relation of being congruent. So let us just do examples. If you take d equals 2, so what does division with remainder when you divide by 2 mean? You can either get a remainder of 0 or a remainder of 1. So what are the various numbers? If I have a number n, let me tabulate the remainders that I get on division by 2. So if I have 0, 1, 2, 3, 4, 5 and so on, so I could also write them out for the negatives. So observe that if I have an even number 0, 2, 4, 6 and so on, when I divide those numbers by 2, of course they leave a remainder of 0. Okay, so these guys would give me a remainder of 0 on division by 2 because they are all even numbers, whereas the odd numbers when I divide by 2 would give me a remainder of 1. Okay, so there are only two possible remainders, and if I sort of collect together all numbers which give me a remainder of 0, that gives me the evens, and the ones with remainder 1 give me the odds. So observe that if so n is even would mean the following, if and only if n is congruent to 0 mod 2, right. So remember, what does this mean? That if I divide n by 2, the remainder I get is the same as what I get when I divide 0 by 2. Okay, so when I divide the number 0 by 2, of course it leaves remainder 0. Similarly, the odd numbers have the property that they give you a remainder of 1 when I divide by 2. And another way of expressing it is as follows: n is odd is the same thing as saying that n is congruent to 1 mod 2. Okay, so the remainders are odd here, remainders are 1. And there are also other things. You can also express relationships amongst numbers. For instance, 3 and 7 are congruent to each other modulo 2. Okay, that is just saying that the remainders are the same when you divide both of them by 2. Okay, in this case the remainder is a 1. Similarly, 10 is congruent to 100 if you wish, modulo 2. because both give you remainder 0. Okay, so and so on. You can sort of see how this concept works by working out many examples and look at the possible remainders, and now we will write out all the values of n. So the remainders are, in this case, when I divide a number by 3, I can either get 0, 1 or 2 as remainders. And let's do the table a little differently. Let me now write down all values of n which would give me a remainder 0 on division by 3. Of course, that just means that n is a multiple of 3. So what numbers would give me 0 when I divide by 3? It's just 0, 3, 6, 9 and so on. That's the list. Now similarly, if I want a remainder of 1 on division by 3, then well, here are those numbers. If I take 1, 4, 7, 10 and so on. Similarly, I could do things on the negative side as well. So here for instance the preceding number is -2 and so on. Okay, all these numbers, observe, when you divide them by 3 give you remainder 1. Okay, similarly here I have 2, 5, 8, 11 and so on. Okay, and observe there is a very easy way of getting these guys. So once you know one of them, which is a 1 here, you just get the rest by adding multiples of 3. Okay, so I add 3, I get 4, I add 3 again, I add 3, subtract 3 and so on. So all these numbers just differ from each other by multiples of 3. Okay, so observe sort of an easy observation here. If m and n are congruent to each other mod d, okay, in other words they both give you the same remainder, here's an alternate way of saying this. This is the same thing as saying that d divides their difference. Okay, so we are already seeing it by example in this case. If I take any two numbers which give me the same remainder, so I take any two numbers for instance in the second row here, they both give me remainder 1, their difference is always a multiple of 3. Okay, so the difference very much is going to be divisible by d, and it's very easy to see why this is true. So let me just briefly sketch the proof and leave it for you to complete formally. M, let's say m gives you some remainder. M is, let's write it out as qd plus r. Okay, r is a remainder when m is divided by d. Similarly, if n is divided by d, I get, let's say, some other quotient q prime, but the remainder is the same. Right? That's what being congruent means. So here's what I have, and now observe, if I subtract m minus n, the remainders will just cancel each other, right? So the r cancels the r, and what's left is just a multiple of d. Okay, so that's the sketch of the proof why when two numbers are congruent to each other, their difference is divisible by d. Okay, and there are lots of other interesting properties of congruences, especially so let me just single out a few of them, specifically related to addition and multiplication. So if m is congruent to m prime mod d, and let's say n is congruent to n prime mod d, then here's what I can say: the sum of these two numbers m and n is congruent to the sum of the other two numbers m prime and n prime. Okay, so the congruences respect addition is one way of stating this. Similarly, I can also put minus there if I wish, or multiplication. If I multiply m and n, it's again going to be congruent to m prime n prime. Okay, so these are very easy to prove, and I leave them as exercises for you, but they have very they're really useful. They have very interesting consequences. They also make computations with congruences very, very simple. Okay, so for that reason this addition and multiplication properties are extremely important. So this whole business of congruences has this rather so here's a pictorial point of view or how one should think in terms of pictures when one thinks of congruences modulo d and so on. So observe that one possible pictorial representation of the set of integers is just as points on the number line. Okay, so this is one of our standard pictures when we think about integers. You just draw a number line and mark off things at equal intervals, and you think of integers as being represented by this. So one nice thing here is this picture also tells you how to do addition, for instance. So if you wanted to add 2 and 3 sort of only using this picture, here's what you would do. You would start with one of the two numbers. Let's say you start with 2 and you go 3 steps from there, right. So 2 plus 3 gives you the number 5. Pictorially becomes the following: you start at say 2 and then you take 3 steps. So 3 steps would mean 1, 2, 3, and where you land is exactly the answer. So 3, 4, 5. So that's going to be what you get when you add 2 with 3. Okay. So addition really represents moving along those many steps starting with, let's say, one of the two numbers. Now similarly we want to think of integers modulo d, for instance. So let me do it again by example. Let me look at integers modulo 4. So I will take d equals 4 just as an example, just makes the picture easier. So how should one really think of these guys? You should think of them as being points on a circle. Okay. So when I say integers modulo 4, what does it mean? When I divide a number by 4, I can either get remainder 0, 1, 2 or 3. So there are 4 possible remainders. So I will think of it as being 4 points equally spaced on the circle. So here, for instance, since I have 4 points, they are just going to occupy the 4 axes. So think of this as the number 0 on the circle. This is the number 1, that's the number 2, this is the number 3. And now what happens? Well, I keep going, think of the next number, which is a 4, but what I am doing here is only keeping track of remainders that I get when I divide integers by 4. Okay. So when I take the number 4, well, 4 when divided by 4 gives me remainder 0. So I should really think of 4 as again being the same point. So this is really also represents 4 if you wish. And then I go one more step, I go to 5, but I don't think of 5 as 5 but only as what I get when I divide it by 4. Okay, what is the remainder obtained when I divide 5 by 4? Well, that's a 1. Okay, so I should really think of 5 as sitting here. Similarly, I should think of 6 as sitting here, 7 as sitting here, 8 as sitting here, and so on, 9, 10, 11, and so on and so forth. So you should really think of the set of all integers as somehow having been wrapped around the circle in this fashion. So when you keep going round and round, you still get all the integers except that many of the integers occupy the same spot. Okay. So that's really how you would want to think of integers when you go modulo something. Now the nice thing with this is you can actually, just like I talked about how addition has a nice interpretation in terms of the picture, you can also think of addition modulo 4, okay, or multiplication modulo 4. So what does addition modulo 4 mean? So let's do this. Let's draw the table for addition modulo 4. So what does it mean to draw the table? Well, I will draw, so let me think of two numbers m and n. 2, 3, 4. So that's the table. Now m and n are integers, but I only keep track of things modulo 4, which means I only worry about remainders. So let me say m is numbers between 0 and 4, 0 and 3, n can take values 0, 1, 2, 3. And now I want to add them, except when I write the answers down, I will only write down the remainders that the answers give me. For instance, so let's do one of the, well, let's do the first row for instance. If I had 0, 0 plus 0 is of course a 0, 0 plus 1 is 1, 0 plus 2 is 2, 0 plus 3 is 3. Similarly, I add 1 to everything, 1 plus 0 is 1, 1 plus 1 is 2, 1 plus 2 is 3, and now 1 plus 3, which is supposed to be a 4, right. So if I were sort of just doing regular integers, I would think of that as a 4 because I am adding 1 and 3, but now I am doing things modulo 4, which means I only look at the remainder that I get. So this answer 4, when I divide it by 4, it gives me a remainder 0. So this guy should really be a 0. So similarly, if I add 2 plus 0 is 2, 2 plus 1 is 3, 2 plus 2 should be a 4 morally, but a 4 is really a 0 because that is a remainder. Similarly, 2 plus 3 is 5, but 5 when divided by 4 gives me remainder 1. Okay, so similarly this is 3, 0, 1 and 2. Okay, so this is what the addition table modulo 4 means. And observe that in fact this has the exact same interpretation as the interpretation for addition that we talked about on the number line. Okay, so for instance, let me pick on something here. 3 plus 3 was 2 according to this, right. So 3 plus 3 is a 2. So this is modulo 4. So that is the equation. 3 plus 3 is actually a 2. Now let us see what that means. So let us start on this circle. So what are we supposed to do? We start at 3. So that is the starting point, and then we go 3 steps. Okay, and wherever we land up is the answer. So here is the starting point. Now going 3 steps has to be done on the circle, right. So I go 1 step, 2 steps and 3 steps. So I traverse 3 steps along this circle, and when I do that, well, I land up exactly at 2. Okay, so when I say 3 plus 3 is 2, what it means is I need to really traverse my distances on the circle rather than think of it as distances traversed on the straight line. Okay, so that is really the addition table. And similarly one can do a multiplication table. You can write out products of numbers and only worry about what their remainders are. So similarly let us do the multiplication table here. So I will write out these numbers n and n as before. Okay, so 0 times 0 is 0, well 0 times anything is a 0, so that is easy, it is all zeros. Similarly, anything times a 0 is a 0. Now let us do 1 times 1 is 1, 1 times 2 is 2, 1 times 3 is 3. Similarly 2 times each of these guys, 2 times 1 is 2, 2 times 2, so what is 2 times 2? Well, morally it is a 4, but a 4 as we just said modulo 4. So I am doing this multiplication table mod 4. Okay, 4 when I look at the remainder it gives on division by 4, that is a 0 again. So that is a 0, and 2 into 3 should really be a 6, but 6 when I divide by 4 gives me remainder 2. Okay, so here it is somewhat funnier, it is 0 2 0 2, those are the four numbers. And similarly if I multiply 3 by each of these, 3 into 1 is 3, 3 into 2 is 6, but 6 is really a 2 modulo 4, and 3 into 3 is 9, and 9 modulo 4 is a 1. Okay, so here is the multiplication table modulo 4 if you wish. And of course if you just literally write it out, it seems somewhat funny to give you funny answers. So for instance 3 into 2 is 2, right. So we get things like this, 3 into 2 is actually a 2. Okay, but remember this is all modulo 4, we are not writing out things for just regular integers. But here there is already something very interesting. If you sort of observe what happened right here, we had these two numbers 2 and 2, right, we multiplied them together and what we actually got is a 0. Okay, so this is already a very new and interesting phenomenon that has popped out of this new arithmetic. So this way of doing things is what is called modular arithmetic. Okay, it is like regular arithmetic in the sense we do addition and multiplication, but the rules for addition and multiplication are more rules on the circle, okay, rather than rules on the straight line. So here for instance if you multiply 2 with itself the answer is a 0, why is this very counterintuitive? Well, we are always used to thinking of numbers as having the following property. So if for instance this were the number x, say some real number, this is a non-zero number, right. So 2 is of course not 0, it is a non-zero number, but when you multiply it with itself it gives you a 0, okay. So observe, we also looked at things like this back when we talked about matrices. If you have a 2 cross 2 matrix A, it was perfectly possible for A to be non-zero, but A times A to give you the 0 matrix, okay. So non-zero things can have square 0. Here is again another somewhat different example in the context of modular arithmetic, where something squares to 0 but the thing itself is non-zero, okay. So some strange things tend to happen in this business. And so one last thing which is again related to multiplication is powers. So what do I mean by this? We could take for instance d to be 5, and let us do the following, let us write out all powers of 2. Okay, you keep raising 2 to higher and higher powers, and what do you study? Well, you study the remainder that you get when you go modulo 5, okay. So what I am going to do is the following, I am going to write out all powers of 2, 1, 2, 4, 8, 16, 32, 64 and so on. So I write those down, and below what I do is I write out the remainders when I go modulo 5, okay. So this is now going to be the remainders modulo 5 or on division by 5. So 1 when divided by 5 gives me remainder 1, 2 when divided by 5 gives me remainder 2, 4 gives me a 4, that is easy. 8 when divided by 5, well 8 is 5 plus 3, so it gives me remainder 3. Okay, so I have 1, 2, 4 and 3. Now let us do the next one. 16 when divided by 5, 16 is 1 more than 15, 15 is a multiple of 5, so it is a 1. 32 is, well, remainder 2, 64 is remainder 4, and let us see what is the next one. 128 is remainder 3 again, okay, and so on. So if you keep continuing this, here is what you will find, that it just keeps repeating like this, 1 2 4 3, 1 2 4 3 and so on, it repeats in a block of 4. Okay, so there is a, so this repeats. Now this is a very good thing to try out oneself. So try doing the same thing for other choices of d and for other powers. So instead of 2, even for d equals 5, try the same thing with say d equals 3, I am sorry, this number instead of 2 think of it as 3 or 4 and so on. And similarly change this number d and see what happens. So in all instances you will always see that it repeats after a certain block size, but it is interesting to study when does it repeat, what is the size of this block that repeats in each case, okay. So I am going to leave this without saying too much more beyond this. There are theorems such as what is called Fermat's little theorem and so on, which are relevant in this context, but for now I would say this is quite a ripe thing for experimentation. So experiment with various choices of d and with various numbers here, okay, and try and make your own conclusions on what seems to be happening here. What are the remainders, when do they repeat, with what repetition size do you get, and how does things change, how do things change if d is say a prime number, say 5 or 7 or 11 would behave in a certain way as opposed to numbers which are not prime, okay. So consider those two cases and experiment with this and see what you get.